T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff. Liftoff. 30 minutes after the control and liftoff.
Hello, everybody. Welcome to another edition where we ask, hey, what's up with the universe? I'm your host, Elihu, and I want to thank everybody who's watching this live. And if you're watching this on a repeat, thank you for ringing that bell so you know when I went live so you can watch this on your repeat. Some little schedule there, so up there on that side of the page. Forgot a little inverted here. Hey, it's Wednesday. Who cares, right? Well, some people do care. Yeah, what's up, everybody? Today, we are actually going to be talking about some recent news. Yes, the Sentinel-6 micro-Frelix satellite launch. Yes, it actually happened on Saturday, November 20th at 9:17 a.m. Pacific Standard Time, which is at 12:17 p.m. Eastern Standard Time for all of you East Coasters out there. So, hey. The Sentinel-6 satellite, it was a joint U.S.-European satellite built to monitor global sea levels launched Saturday. It's about the size of a small truck, and it will enhance weather forecasts and provide detailed information on large-scale ocean currents. Yeah, check this out.
5, 4, 3, 2, 1, 0. And liftoff of Sentinel-6 micro-Frelix, continuing a legacy of ocean observation and international collaboration to benefit all humanity.
And Monday propulsion is nominal.
A beautiful shot there from the first stage looking down towards Earth. Beautiful clear skies there from Vandenberg on the ground. Able to track with that rocket as you see it on screen now. Booster separation is there, visible on screen now. Beautiful shot.
Stage 1, booster burn started.
Here it comes. There it is. So perfectly, just there's the sonic booms we talked about, and touchdown.
The entire world is expecting great things from Sentinel-6, and I know that you will deliver. Go Sentinel-6.
Go Sentinel-6, yes. Sentinel-6, it's about the size of a small pickup truck. You can see right here, it's a little artist's interpretation. It's going to extend about nearly 30 years of continuous data sets on the sea level collecting by an ongoing collaboration of U.S. and European satellites. Of course, it's going to enhance the weather forecast. And it also helps provide detailed information on large-scale ocean currents to support shipping navigations near coastlines. So that way they can actually find out where the shipping lanes are because large mammals like whales avoid them. That way it'd be safe for the environment as well. Hey, win-win situation, right? Pretty awesome sauce. The Sentinel-6 Jason CS mission, it's a part of Copernicus, the European Union's Earth Observation Program, managed by the European Commission, continuing the legacy of the Jason series missions. The Sentinel-6 will extend the records of sea level into the 4th decade, collecting accurate measurements of sea surface height for more than 90% of the world's oceans. And they also can provide crucial information for an operational oceanography, marine meteorology, and climate studies. The twin Sentinel-B is scheduled to launch in 2025. The spacecraft is named for Michael Freilich right here. He's the former director of NASA, Earth Science Division, who was a huge leading figure in advancing ocean observations in space. Mr. Freilich passed away on August 5th of 2020 this year. That's why the satellite was named in his honor, of course. Yeah, that's always an honor. The sounds, next one we're going to talk about. Yes, sorry. Today we are actually talking about a little hodgepodge of science. I forgot to mention that earlier. This is some stuff that, this is basically some recent news, science news here. The sound of perseverance. It is the first rover that's rigged with microphones. The probe is on its way to Mars right now, and it picked up a subtle sound of its own inner workings during interplanetary flight. I wonder if you can hear that. This is the actual sounds of perseverance, of listening to dead space. See, space isn't quiet. The microphone aboard NASA's Mars 2020 Perseverance rover recorded the sounds of space basically hurled. Another microphone aboard the rover is indeed specifically to listen for the laser zaps of the SuperCam instrument. This one is developed to capture some or all of the entry, descent, and landing sequence from the rover itself. Data from that 60-second audio file was collected on October 19th. I can't talk. Excuse me for a second. October 19th, during an in-flight checkout of the camera and microphone system that's going to pick up the landing on Mars in the Jezero crater of early next year. Excuse me for a second. Invisible drink, yes. This is the Mars Perseverance rover. A little diagram here. Everybody at NASA basically nicknamed it Percy. It's about a car-sized rover designed to explore the Jezero crater on Mars as part of NASA's Mars 2020 mission. Sorry, if you're reading the comments on this thing, on the comments on the live of the review, you see why I'm laughing. Thank you, Bees Nest. Haha. What was I saying? Oh yeah, I was talking about Percy. It was manufactured by the JPL and it was launched on July 30th of this year at 7:50 a.m. Eastern EDT. It's scheduled to land on Mars on February 18th, 2021. Let's get a little bit of look at this little probe here. The key objective, basically, for Perseverance mission on Mars is astrobiology, including the search for ancient microbial life. See, I told you I can't talk today. Basically, the rover will characterize the planet's geology and past climate, and it's going to basically pave a way for human exploration. It's going to collect some Martian rock and regolith. Oh, if you want to refresh on what regolith is, it's broken rock and dust. Basically, the mission, it's currently under consideration by NASA in cooperation with the ESA. They're going to think about sending a spacecraft to Mars to collect these samples after they actually gather them and test them out. They actually want to get a rover, send a rover to Mars, to Mars, bring back those samples here. I mean, they already have it analyzed, but they actually want to physically look at it, which I'm looking forward to this. Hey, did you know that there is a missing link that has been solved? Yeah. A 16-year-old cosmic mystery link has actually been solved. The Blue Ring Nebula. Yeah. You guys probably saw this little retweet of mine here. This is what I'm talking about today. It's actually perplexed scientists for about 10, 11 years or so. And it basically appears to be the youngest known example of what two stars merging into one is. It's very rare star system that's actually been found in our own Milky Way galaxy. But it is doomed to end in a big, huge, massive explosion. Yep, something we can actually see with the naked eye. But it's located 8,000 light years away, which means if it explodes, tomorrow we won't see it for 8,000 years. So, hey. if humans are still around, we'll be able to see it. I mean, this configuration, it's so rare that astronomers never expected to find a star like this in our own galaxy. This is called a Wolf-Rayet star system. I mean, only some massive stars evolve into what is known as the Wolf-Rayets as they approach the end of their lives. But the lifetime of a star that is very short, the astronomer said. In 2004, NASA's space-based Galaxy Evolution Explorer, the GALEX, spotted an object unlike anything they've ever seen in the Milky Way galaxy. It's a large, faint blob of gas with a star at the center. In the GALEX images, the blob appeared blue, though it doesn't actually emit light visible to human eyes, so they end up, they reveal a thick ring structure within it. So the team nicknamed it basically the Blue Ring Nebula. Somebody, I forgot who mentioned on Twitter, they called the Cone Star Nebula. Do black holes get bigger the more they consume? Well, we're going to talk about that actually a little bit at Bee's Nest. And yes, they technically do get bigger the more they consume. A new study published online. Yeah, this is the question he asked. There was a new study published online on November 18th in the journal Nature. May have cracked the case by applying cutting-edge theoretical molecules to the slew of data that has been collected on this object. The authors post that the nebula, a cloud of gas in space, is likely composed of debris from two stars colliding and merged into a single star. I hope that wasn't too complicated for you. Let's actually check this little video out here. It explains a little bit more better. Okay, bad English. While merging star systems are likely to fairly common, they are nearly impossible to study intermediately after they form because they are obscured by debris that the collision kicks up. I mean, once the debris has cleared, at least hundreds of thousands of years later, yeah, it's a long time, the channeling to identified because they resemble non-merged stars. This Blue Ring Nebula here, it appears to be the missing link. Astronomers are seeing a star system only a few thousand years after the merger, when evidence of this union is still plentiful. I mean, it appears basically to be the first known example of a merged star system at this stage of existence. Operation between 2003 and 2013, of course, managed by JPL. GALEX was I can't talk. I told you. GALEX was designated to help study the history of star formation throughout most of the universe by taking the census of young star populations of other galaxies. Basically, phantom planets. In 2006, GALEX team looked at the nebula at its 20-inch Hale telescope at the Palomar Observatory in San Diego. And then they saw, using another more powerful 10-meter telescope at the W. Keck Observatory in Hawaii, they found evidence of a shockwave in a nebula suggesting the gas exposing the Blue Ring Nebula has indeed been expelled by some kind of violent event around the center star. Yeah, Keck actually suggests the star is pulling a large amount of material into its own surface. But they had no idea where this material was coming from. So, of course, in 2012, using the first full-light sky survey from NASA's Wide Field Informed Survey Explorer. I always call it WISE, sorry. Sometimes it's hard to pronounce, so that's why I love the acronyms. It basically, the GAC team identified a disk of dust orbiting closely around the star. Of course, WISE was adapted in 2013 as the asteroid hunting NEO-WISE mission, in case anybody wants to know. Basically, past data from other 3 infrared observations, including Spitzer telescope, also spotted this disk. I mean, they didn't just use one and say, okay, it's there. No, they had multiple observations. So it's like, okay, this is confirmed. We see this, you see this, we see this. 3 different telescopes confirmed this. Of course, they didn't rule out the possibility that a planet was also orbiting the star. Hey, you never know, right? But of course, the team will eventually show that the disk and material expelling into the space coming from the same larger than even a giant planets. Let's see. We're gonna take a short little break while I get something to drink here, and play a quick little commercial. Okay, be right back.
Hey guys, LDG Pixels here. If you have issues with your computers, have any IT questions, come join us at YouTube at LDG Pixels. That's on YouTube, LDG space Pixels. News, nerd chat, help you fix up your computer, free.
And we are back. Hopefully I can talk now again. Okay. Our next topic we are going to discuss is called the Roman Space Telescope. Yes. It's used to uncover the echoes of the universe's creation. The Wide Field Infrared Security Telescope, otherwise known as W-FIRST. I remember that one. It was basically renamed the Nancy Grace Roman Telescope on May 20th, 2020, after her passing. And I will get into Mrs. Grace in a little bit about that. The Nancy Grace Telescope, it's going to detect vestiges of sound waves that once rippled through the primordial cosmic sea. Yes, we got a space satellite for this now instead of a ground-based telescope that wasn't pigeon droppings. Some people know what I'm talking about, so. According to these new simulations, the Romans' observations could extend these measurements into an unprobed epoch between the universe's infancy and the present day. Basically, studying the echoes from this era will help us trace the evolution of the universe and hopefully solve some pressing cosmic conundrums. Hopefully, I said. Sound waves from the nascent universe called baryon acoustic oscillations, BAOs. Yeah, I'm going to say BAOs from now on, okay? They're called baryon acoustic oscillations. So BAOs. If you hear me say BAOs, that's what I'm referring to. They left their imprint on the cosmos by influencing galaxy distribution. Researchers have explored this imprint back to when the universe was about 3 billion years old, or roughly 20% of its current age at what scientists configure to about 13.8 billion years old. It's the same epic Roman BAO studies that are optimized to investigate. Of course, now our team of scientists has demonstrated that the mission could be even further back in time to explore the impressions left by BAOs. This animation, it explains
immediately after the universe was born. It was
wrong one. This animation here, it explains how BAOs arose in early universes and how astronomers can study the faint imprints they made on galaxy distributions. Just here, this guy explains it better from NASA, so check this out.
Immediately after the universe was born, it was too tiny and too hot for protons, electrons, and even photons to exist. Within a second, it had expanded and cooled enough for protons and neutrons, collectively called baryons, to form. Almost instantly, there was a rapid burst of sound waves, triggered by tiny variations in this particle soup. Scientists call these waves baryon acoustic oscillations. The pressure waves traveled outward for 400,000 years, until the universe thinned and cooled enough for light to travel through it. The universe became transparent, and the waves froze in place. Over time, the denser regions formed by the waves encouraged more star and galaxy formation than other areas. The imprint of those waves expanded with the universe, slowly accelerating due to dark energy. Today, with our snapshot of the universe, there is a slight tendency for galaxies to be separated from each other by a distance related to that expanding ring radius. Although difficult to see, it is detectable as a slight bump through careful surveys of many galaxies.
Okay, hopefully that little explained a little bit for you, but the Nancy Grace Roman Telescope, its primary mirror here. This is huge. It's going to collect and focus light from cosmic objects. Let me show you what it actually looks like so you actually know what I'm talking about. This mirror here, this is not a flag. This is a mirror. Yes. It's going to collect and focus light from cosmic objects near and far. And it has been completed. Yes. Using this mirror, the Roman telescope, it's going to capture with a field of view of 100 times greater than any Hubble images. I am excited about this. I mean, Roman, it's going to appear through dust and all across vast stretches of space. It's going to study the universe using infrared light, which the human's eyes can't see. Unlike the Hubble is very limited infrared spectrums, but it's basically red, blue, and green lights. I'm going to do a video on Hubble in the future, so you can stay tuned for that. The amount of detail these observations are going to make, it's going to reveal directly related to the size of the telescope's mirror. Of course, since the larger surface gathers more light and measures finer features. Let's see. Now, we are going to talk about another subject here. What is dark energy? I know. Scientists have actually discovered a mysterious pressure dubbed dark energy. They say it makes up about 68% of the total energy content of the cosmos. But so far, we don't know that much about it. I mean, exploring the nature of dark energy, it's one of the reasons that NASA is building the Wide Field Infrared Survey Telescope, the WFIRST. It's a telescope whose measurements will help illuminate the dark energy puzzle. And with a better understanding of dark energy, we're going to have a better sense of the past and future of the evolution of the universe. I mean, nobody knows exactly what dark energy is. More is unknown than known. But of course, theorists chase down a couple of possible explanations. Cosmic acceleration could be caused by new energy components, which would require some adjustments to Einstein's theory of gravity. Of course, perhaps the cosmological constants, which Einstein called his biggest blunder, is real after all. Hey, who knows? Einstein wants to be proven wrong like every scientist. It's like, hey, am I right? Am I wrong? Okay, I'm wrong. Thank you. Correct me. How was I wrong? Every scientist admits to his fault or his or her fault. Alternatively, Einstein's theory of gravity, it may break down on cosmological scales. If this is the case, that theory needs to be replaced with a new one. Of course, that it has to incorporate the cosmic acceleration we already have observed. Theorists still don't know what the correct explanation is, but WFIRST hopefully help us figure this out. Here's another little clip from NASA about this.
What makes up most of the cosmos? Not stars or planets or even atoms. It's something scientists call dark energy. And so far, no one has a good handle on what it actually is. Dark energy, first discovered in 1998, is an enigmatic pressure pushing the universe apart at an ever faster clip. Scientists suspect it began flexing its muscles around 5 billion years ago. Beyond that, we know very little. Learning more about dark energy is one of the primary reasons NASA is building WFIRST, a new space telescope whose measurements will help us home in on this mysterious cosmic component. Without a better understanding of dark energy, our knowledge of the past and future evolution of the universe is incomplete. WFIRST will tackle the dark energy problem using different yet complementary wide field surveys. A key aspect of them is a measurement called redshift. Because space itself is expanding, the farther we look, the faster galaxies are moving away from us. This results in a measurable shift in an object's light toward redder colors. This redshift indicates how fast the expanding universe is carrying galaxies away from us. If we can also figure out a galaxy's distance by other methods, we can use both pieces of information to measure how the universe expanded while the galaxy's light was traveling to us. WFIRST will map out the positions and distances of millions of galaxies. This will allow astronomers to see how the distribution of galaxies has changed, revealing how dark energy has evolved over cosmic time. An alternative way to measure dark energy is by using exploding stars called Type 1a supernovas. These blasts are caused by the total destruction of a white dwarf star, and each one emits similar amounts of light. But the farther away they are, the fainter the explosions look. By measuring how bright Type 1a supernovas appear to be, we have a way to measure their distances. It was by comparing supernovae redshifts to their apparent brightness that astronomers discovered dark energy. These studies show that explosions at greater redshifts were dimmer than they should be in any model where the expansion of the universe was not speeding up. WFIRST will study thousands of explosions, reaching to even greater distances to measure dark energy's influence over time. work of the early universe provides another way to pin down dark energy. In its first 500,000 years, the universe consisted of a hot, dense, expanding fluid. Small density changes in the fluid excited sound waves that traveled throughout it. Although the waves, called baryonic acoustic oscillations, eventually ceased, astronomers have observed their faint imprint in the way that galaxies cluster together. This provides another way to measure galaxy distances. W1st will measure how this imprint changes through cosmic history, allowing astronomers to map the expansion of the universe in more detail and probe dark energy's effects over time. With each technique cross-checking the other, W1st surveys will peer deeply into dark energy, providing important data to help scientists figure out what exactly it is and how it will determine the ultimate fate of the universe.
Yes, hot plasma soup. I mean, for most of the first 500,000 years, the universe looked extremely different than it does today. Instead of being speckled with stars and galaxies, the cosmos was filled with a sea of plasma, charged particles that formed a dense, almost uniform fluid. Of course, there was tiny fluctuations in about 1 part in 100,000. With a few variations it took the form of a slightly denser kernels of matter, like a single ounce of a cinnamon sprinkled onto about 13,000 cups of cookie dough. Yeah, that's a good little analogy, right? Since the clumps had more mass, their gravity attracted additional material. It was so hot there. Yeah, how hot was it? It was so hot that particles couldn't stick together when they collided. They just bounced off each other, alternating between the pull of gravity and the repelling effect created waves of pressure, sound, that propagated throughout the plasma itself. Of course, over time, the universe cooled and particles combined to form neutral atoms. Because of this, the particles stopped repelling each other. The waves ceased. Their traces, however, still linger in the echoes of the cosmos. You guys remember the cosmic radiation background. W1st will illuminate dark energy. I mean, previous missions, they gathered some clues, but so far they haven't got any results that either weakly or strongly favor one exploration over another. With the same resolution as Hubble cameras, but of course this one has a wider field. It's 100 times larger. This W1st is going to generate never before seen big pictures of the universe. It's going to, if you guys are unaware, it's going to advance exploration of dark energy mystery. Of course, in the only ways that other telescopes can't, by mapping how matter is structured and distributed throughout the cosmos. And also by measuring large numbers of distant supernova, or supernovae, however you want to pronounce it. Of course, these results will indicate how dark energy acts across the universe and how it has changed over cosmic history. The mission will use 3 survey methods to explore an exploration of dark energy. It's the high latitude spectroscopic survey. Oh my gosh, these being accused NASA words. That's why I love acronyms. HLSS. It's going to measure the accurate distance and positions of millions of galaxies using a standard ruler technique. Measuring how the distribution of galaxies varies with distance will give us a window into the evolution of dark energy over time. The study will connect the galaxies' distances with the echoes and sound waves just after the Big Bang. It's also going to test Einstein's theory of gravity over the age of the universe. I mean, W1st will also conduct a survey, one of the type of exploding stars built on observations that led to the discovery of accelerated expansion. I mean, Type 1A supernovas, take them for example. They occur when white dwarf stars explode. They generally have the same absolute brightness at their peak, making them so-called standard candles in the universe. That means basically astronomers can determine how far away they are by seeing how bright they look from Earth using the Doppler effect. And the farther they are, the dimmer they appear. Astronomers can also look at the particular wavelengths of light coming from the supernovas to find out how fast and dying the stars are moving away from us. Basically, by combining these distances with brightness measurements, Scientists will be able to see how dark energy has evolved over time, providing a cross-check with the 2 high-latitude surveys. Of course, additionally, the high-latitude imaging survey will measure the shapes and distances of multitudes of galaxies and galaxy clusters. The immense gravity and mass of objects warp space, time. Yeah, it actually does. The immense gravity of massive objects actually warp space and time. Einstein proved that. This also causes more distant galaxies to appear distorted. Basically, observing the degree of distortion, it allows scientists to infer the distribution of mass throughout the cosmos. This includes all the matter we can see directly, like planets and stars, as well as dark matter, another dark cosmic mystery, which is only visible through its gravitational effects on normal matter. This survey is going to provide an independent measurement of the growth of large-scale structure of the universe and basically how dark energy affects the cosmos. Hey, dude, what the hell are you doing, man? I told you about this. Come on, man.
Hey, what's happening? This is Corin Nemic. I'm talking to you from my backyard. Just signed up for Cameo app. Sean asked and told me that's what all the cool kids are doing. Just trying to be one of the cool kids. But I am dedicated to this. Dedicated to leaving you a message, no matter what the conditions are. That's why I'm doing this in the rain, to prove to you how serious I am about this. I mean, I will give you a shout out from a train. You know, I'll give a shout out to you while I'm on a plane. I'll give a shout out to you from a car. I'll give a shout out to you from a dive bar. In fact, I heard that David Faustino's on here as well. He said that he was going to give some weird and creepy shout outs, but I challenge him. You want a weird and creepy shout out? Came to the right place, buddy.
Dude, sheesh. Why did I interrupt, man? Sheesh. Talking about plasma. Okay. Well, let's get back to the plasma here. Basically, discovering how dark energy has affected the universe expansion in the past, it's going to shed some light on how it will influence expansion in the future. If this continues to accelerate the universe expansion, we may be destined to experience a big rip. Yeah. Instead of a huge freeze, it'll be a big rip. In this scenario, dark energy will eventually become dominant over the fundamental forces. Basically, that means causing everything that is currently bound together, galaxies, planets, people, pets, plants, basically break apart. Yeah. Exploring dark energy, it's going to allow us to investigate and possibly even foresee the universe's fate, hopefully. Of course, that's billions of years from now, so hey, I'm going to be dead before then. So are you. Sorry about that, but that's some sad news. We're not going to be around to see that. But what about frozen echoes? I mean, when atoms formed, the ripples essentially froze in place, carrying with them a little bit more than a matter of the average across the universe. With the repulsive pressure of the plasma gone, gravity became the dominant force. About a couple 100 million years it took for clumps of plasma that once filled the universe slurped up more material to become stars. Yeah, I said slurped. The mutual gravity pulled stars together into groups, ultimately forming the galaxies we see today. Yeah, look up, you see wondrous things. Of course, slightly more galaxies formed along the ripples than elsewhere. While the waves no longer propagated, the frozen ripples stretched as the universe expanded, increasing the distance between galaxies. You know, by looking at how galaxies are spread, but in different cosmic epochs, we can actually explore how the universe has expanded over time. Scientists have noticed a pattern, basically, in which way galaxies cluster together from measurement of the nearby universe. Let me repeat that. Scientists have noticed a pattern in the way galaxies together form measurements of the nearby universe. Any galaxy today, we are more likely to find another galaxy about 500 million light years away than slightly nearer or farther. But by looking out into space, you gotta look up to early cosmic times, means that this distance is the vestige of the frozen bowel rips will decrease. The Roman probe, it's going to extend previously research by mapping the expansion of the universe. The Sapani and his team show that Roman surveys were able to probe for Bow's remnants 5 times farther than originally planned, back when the universe was only about 600 million years old. You know, just about 4% of its current age. Not that old, just a little baby. Learning more about the way that the cosmos has expanded over time, it's going to allow scientists to explore dark energy. It's basically a mysterious pressure that is accelerating the expansion of the universe. Yeah, dark energy. The Roman probe is opt to survey the cosmos of bow impressions across the middle of its current age, because that's when scientists think dark energy transitioned from being a minor contributor to the contents of the universe to the most dominant force. But sometimes scientists do theorize and hypothesize about dark energy activity when the universe was much younger. I'm going to quote this quote here. Jason Rhodes, a senior research scientist at NASA's JPL, said this: "We haven't extensively explored Bow's imprints from when the universe was very young because we need an enormous sample of galaxies to do so. That's where Roman comes in. The mission has such a wide field of view that observation like this will become possible." Next, we are going to talk about some very sad news in the news that was reported recently. The Arecibo telescope. Yes, I know. If you haven't heard the sad news yet, the Arecibo telescope is going to be demolished. It's been a radio telescope used for many, many astronomical research projects. I mean, including the search for studies for pulsars, mapping atomic and molecular gases in the galaxy. The NSF, National Science Foundation, sorry, me and acronyms again, they announced a plan for controlled decommissioning of the 305-meter radio telescope on November 19th to protect the health and safety of those who work at and visit the observatory. Oh, this is very sad news. But, you know, they did make some very remarkable discoveries, so let's actually take a look at a few of them. In 1967 and September 2007 and May 10th, Arecibo discovered that the rotation rate of Mercury is actually 59 days, not the previous estimated value of 88 days. Yep, they found out the rotation is not entirely locked, but rather the rate is an orbital renaissance with 2 orbits in every 3 rotations. And I explained this on the very first episode of the tour of the galaxy, a tour of our solar system. I talked about the sun and Mercury. If you saw my video files, you can go back and check that out later. Arecibo in 1968 sent a message from to space with the help of Carl Sagan. The message sent in 1974 toward the globular cluster of M13 consisted of 1,679 bits of information. A 0 is represented by an off radio pulse, while a 1 is represented by an on radio pulse. And if you're interested in learning how to read this message, in the description below, I put a link in how to read the Arecibo message. I could have talked about it. I'm like, I'm going to let people actually read this for themselves, get the little understanding, make sure they understand it better. So if you have any questions, you can always put it in the comments or the chats. In 1974, researchers just using the Arecibo Observatory discovered the very first binary pulsar, in which a pulsar orbits another star. The discovery earned Joseph Tyler and Russell Halsey a Nobel Prize in Physics in 1993. Also in 1981, Arecibo provided the very first radio maps of Venus. At the time, it's basically a planet perpetually covered in clouds. Nobody knew the surface of it, but they actually got it done in 1981 with Arecibo. Also, get this, in 1989, Arecibo named an object named 4679 Callista. We also have the closest planet to the sun. Mercury has the ice. Oh, wait, what? Oh, yeah. Sorry, I'm on the wrong slide here. 1992, astronomer Alexander Wolzexkin. I mispronounced his name. I know that. I know that. Sorry. He actually used the Arecibo telescope to spot 3 exoplanets from a pulsar named PSR B1257 plus 12. These were the very first planets ever discovered outside our solar system. This is sad news for Arecibo. All these wonderful discoveries. Oh, I mean, gravitational waves. Ripples in the fabric of space caused by tremendous events like colliding black holes or supernovas were basically finally confirmed by scientists in 2016. I mean, Einstein predicted this a century beforehand. I put this on here. This momentous discovery made by the LIGO, the Laser Interferometer Gravitational Wave Observatory. See? I love acronyms. LIGO, it's better. 2007, scientists first detected fast radio bursts, FRBs. I mean, this recent evidence suggests that these pulsars are coming from highly magnetic neutron stars, known as magnetars. And of course, despite all these incredible discoveries, Arecibo is most famously found for its use in SETI. If you don't understand what SETI is search for extraterrestrial intelligence, and the disc was even featured in the movie Contact. Of course, no radio signals from aliens have ever been detected by Arecibo nor any other observatory confirmed. There's still theories on the WOW signal. Because, look, basic life, the Drake equation. Yeah, I'm sorry. Yeah, I'll let you pause this for a second while you're watching this so you can actually know what the Drake equation is. It's the number of civilizations using communication technologies that we can detect, equaled by the calculations of what they are. I'll let you read it. Hey, guess what's coming up? There was some news coming up in the night sky. And you won't even need binoculars to see what I'm talking about. Yes. What's visible this month at nighttime or dusk, as some people call it, is Jupiter in the west. Yeah, where's my directions? In the west. Saturn in the west. Mars in the east. In the morning, pre-dawn, you see Venus and Mercury. I mean, 5 planets in the solar system, they're going to be bright enough to see. Throughout the north, look for Mars, Jupiter, and Saturn in nightfall. That bright star in the east, that'll be Mars. The bright star in the western sky, that's going to be Jupiter. Of course, it's not as bright as its neighbor. Saturn will be seen about 5 degrees east of Jupiter, about a thumb's width. Or from the width of 2 fingers at arm's length, basically. Your thumb here close or 2 widths, arm's length. Sorry. I had a little mini one on there. Here it is. Here's how the stars will look in the western sky for you, in case you want to know. November, in the evening time, Saturn, Pluto, and Jupiter. You want to look west. About 1 hour before sunrise in the east, you can see Mercury and Venus. Venus is the brightest, quote-unquote, star in the pre-dawn morning. And it can be Mercury found right below it. Although relatively overshadowed by Venus early, Mercury does brighten and climb higher in the sky as the month progresses. We also have some other news you can see in the sky. Comet Erasmus. Erasmus. Okay, I can't pronounce it or talk today. Every 2,000 years or so, C2020 S3 visits the inner solar system. If you never heard of this before, it's because it was fairly new discovery. Right now, it's at the 7th magnitude and easy to see with backyard telescopes and binoculars, very powerful binoculars. Of course, forecasters believe it'd be more than triple the brightness for the 5th magnitude by the time it dips inside the orbit of Mercury next month. Only if the glare of the nearby sun will prevent it from being visible to the naked eye. I mean, what's different about Comet C2020 S3 or Erasmus? It was named for Nicholas Erasmus. It was discovered. Sorry, yeah, it's about him. At R181 AU Beers Money in 2020, found beyond 5 AU. Okay, I can't talk today. Gerald Ryman, he took this picture Friday morning, November 20th, using a 12-inch telescope in Farm Trivio, Trivoli, Nambia. Yes. He said, quote, "This tail is magnificent. In fact, I couldn't fit it in a single field of view. This 2-panel composite shows the first 3 degrees, and it keeps going well past the edge of the photo. So that's a long-ass tail. It's brightest as it approaches the sun. Right now, like I said, it's at the 7th magnitude, and easy for Skyyard Backyard telescopes to check them out. Which I want to show you guys something here. I am going to show you how you can actually find this. You can always go to skylive.com. Oh, come on, reload page, reload. There we go. Skyload.com. Oh, I didn't hit share yet. Sorry about that. I'm going to show you this right here. Skyload. Come on, there we go. There we go. The sky. I have this set for basically where I'm in San Francisco. You can easily set this anywhere you want. You can hit the change right here. Right now, it tells you exactly the right ascension, declination, and the constellation you can find it in. And how the visibility is. It's above the horizon in San Francisco right now. Visible looking southwest direction. So I'm going to put this little website into the description after this show is over. So you can click on it and check out where the comet is currently at. Yes, I just used a double preposition, didn't I? Oh my gosh. I said where it is at. Wow. Okay, listen, I want to thank everybody here for joining me because I also forgot to show you this right here. Little positions. I've got my little sky chart. Oh my gosh. I am hungry today. That's why. There's a little sky chart. If you can't find Venus, if you can find Venus, you can find the comet. Look low southeast before sunrise. The comet Erasmus is in the constellation Hydra, just to the right of Venus. Neighboring Virgo. The bright star Spica is nearby too, providing another useless reference point. This right here is what you'll see tonight if you happen to go look up southeast. And a little bit higher tomorrow night, you'll see it as well. So I want to thank everybody for joining me today. And just keep asking yourself, hey, what's exactly up with the universe? So I want to thank everyone for joining me live here. And who's ever watching this on the video, on the replay, thank you for clicking that bell so you know when I went live or when you can watch it later. So more science news, follow me on Twitter. And thank you, everybody. And have a good morning, evening, rest of the day, wherever you may be.